This presentation continues our discussion of correlation and regression involving categorical variables and begins our focus on logistic regression. We learned to use multiple regression to predict scores on a dependent variable using an interval or ratio scale of measure. In contrast, we will use logistic regression to predict group membership on a dependent variable using a nominal scale of measure and with two levels. Thus, like multiple regression, predictors in logistic regression can be any combination of categorical or continuous variables. Like chi-square, this procedure has a history of being used in medical research and especially to identify predictors that serve as risk or protective factors of disease states. Also, consistent with chi-square test of independence, we'll discuss the relationship of the predictor to the dependent variable using the odds ratio. This presentation will assume you have seen the discussion of the odds ratio in the chi-square test of independence in the slides that precede this presentation. There are many ways in which logistic regression differs from multiple regression. One big difference is that the logistic regression line is curved rather than the straight linear regression line in multiple regression. There are regression solutions, namely discriminant function, that draws a straight line through data using a categorical dependent variable, but this approach is not used very frequently in psychological research at the current time. In this drawing, the small black dots plot the scores of individuals based on their hours of studying the predictor X and what group they were in on the dependent variable, which was whether or not they passed the test. So the horizontal line of black dots that correspond to the score of 1 on the dependent variable Y are those individuals who were in the target group and passed the test. And the black dots that correspond to the score of 0 on the dependent variable are those individuals who were in the reference group and did not pass the test. The curved regression line connects the probabilities or coefficients predicted for each individual in the sample using the logistic regression equation. Note that the point on the y-axis that corresponds to 0.5. We will discuss this point in more detail in subsequent slides. This image was obtained from the website cited at the bottom of this slide. In multiple regression, the regression equation is used to predict a participant's score on the dependent variable. But in logistic regression, the equation is used to derive a probability or coefficient that ranges from 0 to 1. And this probability is judged against a cutoff score, which most often is set at 0.5. If the probability is equal to or greater than 0.5, then the individual is predicted to be in the target group of the dependent variable. If the probability is less than 0.5, then the individual is predicted to be in the reference group of the dependent variable. Just as the regression line in multiple regression connected all the predicted scores on Y, the curved regression line in logistic regression connects all the probabilities computed for various values of X received by the participants. The probability used to draw the curved regression line is computed by solving for the following equation. The natural log raised to the zth power divided by 1 plus the natural log raised to the zth power. The symbol E refers to the natural log, which is a constant in mathematics, much like pi. The natural log is equal to 2.718 approximately. The unknown in the equation is the exponent z, or the value the natural log is raised to. That exponent is computed for each participant in the dataset by using the logistic regression equation. So we derive an exponent for each individual by inserting their actual scores on all the predictors, multiplying those scores by their regression coefficients, and summing the results with a constant. Instead of computing someone's score on the dependent variable as we do in multiple regression, in logistic regression we use the regression equation to compute an exponent that is inserted into a working equation that results in a probability ranging from 0 to 1. That probability is judged against the cutoff 0.5. If a participant scores 0.5 or above, they are predicted to be in the target group on the dependent variable, and if the individual scores below 0.5, they are predicted to be in the reference group on the dependent variable. Let's take a closer look at how the formula works by looking at a couple of examples. In example 1, the regression equation derived a score of positive 3 for a participant. If we insert 3 as the exponent in the equation, we see that the resultant predicted probability for that participant was 0.95, which exceeds the cutoff of 0.5. And as a result, we would predict this participant was in the target group on the dependent variable. In example 2, the regression coefficient derived a score of -2 for a participant. If we insert -2 as the exponent in the equation, we see that the resulting predicted probability for that participant was equal to 0.016. This falls below the cutoff of 0.5, and we would then predict this participant was in the reference group on the dependent variable. The interpretation of the regression coefficient in logistic regression also differs somewhat from that of the coefficient in multiple regression. First, in logistic regression, B is called the partial logistic regression coefficient. And as in multiple regression, the term partial added to this term indicates we are interested in the unique ability of the predictor to predict group membership in the criterion. Thus, our focus will be on the unique relationship the predictor has on the criterion after partialing the effects of all of the predictors in the model. But because the regression equation is used to derive an exponent, changes in the value of a predictor now have exponential effects on the dependent variable. Thus, B is the change in the exponent of the natural log when its predictor increases 1 unit. A positive B indicates a predictor that increases the odds of belonging to the target group on the dependent variable. We would say such a predictor is a risk factor. Thus, the odds ratio for that predictor will be greater than 1. Conversely, a negative B indicates a predictor that decreases the odds of belonging to the target group on the dependent variable. We would say such a predictor is a protective factor or a resilience factor. The odds ratio for this predictor will be less than 1. When B equals 0, the predictor fails to predict group membership in the criterion, and the odds ratio for that predictor will be 1.